We are now going to look at a very useful application of Chernoff bounds. In this application, we're asked to estimate a particular parameter. And what is this parameter? Let's consider a population. This population has a large number of people, some of whom are cricket fans, and the rest of them are baseball fans. Okay, and everybody likes one or the other, but not both. And we're interested in finding out the fraction of people, the fraction p of people in this world, in this population, who like cricket. So this is our parameter, and this is the parameter that we want to estimate. Now, there is one way we could do that. We could literally go into the population, ask everybody whether they like cricket or baseball, and find out that particular proportion p, the parameter p, based on the responses that we get. But that obviously is not feasible because the world is large. Okay. Instead, we will be resorting to sampling. Okay. So we're going to be sampling n individuals. Okay, and we will, based on the sampling that we do, we will get a certain number of people who will respond saying, "Oh yes, I like cricket," and that is this random variable x. Okay, and that x is going to be some fraction of n. That fraction is this p tilde. Now we're going to use p tilde as an estimate for p. It's not going to be p perfectly, but it's going to be an approximation or a good estimate of p. Now suppose the population is very, very large in size compared to the number of samples that we're going to make. Then in essence, every sample that we draw from the population is going to be independent of other samples that we made. So with that sort of an assumption, we can notice that the random variable x is actually a binomial random variable, because each time we sample, we will be and our success is that the person we ask is a cricket fan, and that success is going to happen with probability p. And therefore and we're going to count the number of such successes, and so this random variable x therefore is going to follow the binomial distribution. As a result, the expected value of x is e of x is going to be n times p. And if you want to draw the distribution for x, it's going to be looking something like that. So its mean is going to be n times p, and the distribution is going to peak at n times p, and it's going to have this sort of a shape. Now the question is, how close is p, the parameter that we want to estimate, to how close is p to p tilde, which is the estimate that we have of p. Notice that this question is not as straightforward as we may like it to be. For example, if we want p and p tilde to be very close to each other, so the difference is at most some epsilon. So let's say we want p minus p tilde absolute value to be at most some epsilon. This is great, but there is always going to be some probability with which such an inequality is going to be violated. So making requiring such a guarantee is not necessarily a good thing. Instead, in such cases, we will have to consider a confidence interval. So let's define what a confidence interval is. So a 1 minus gamma confidence interval, and gamma is going to be some small value strictly greater than 0. The 1 minus gamma confidence interval for the parameter p is an interval around p tilde. So it's basically p tilde plus or minus some small delta, and this delta again is a small value, strictly greater than 0, such that we have this following probabilistic guarantee. And what is this guarantee? The probability that this parameter p lies within this interval is large, in particular greater than 1 minus gamma. So we are interested in a confidence interval for the parameter p with a very small gamma and a very small delta. Okay, let's look at an alternative way to express this confidence interval. Here we're talking about the probability that the parameter p lies within an interval with large probability. An equivalent way of stating that is the probability that it will fall outside of the interval should be small. Let's get the help of this figure to understand this alternative form of the confidence interval. So there are two ways in which the estimate p tilde can be far away from p. On the one hand, p tilde can be so small that n times p tilde is very small, or alternatively it can be very large. So let's focus on the case where n times p tilde is very small. Okay, what does that mean? Well, let's ignore the n, because we're trying to compare p tilde with p, and the n is common, so we can ignore that. Basically, even after you add a delta to p tilde, p is still too far away. That's one reason. I mean, that's one way to interpret the case where p tilde is very small. So that, if we want to formally state that, we will say that that's the probability that p is larger than even p tilde plus delta. Similarly, the other way that p tilde can be too far away from p is if its value is so large that n times p tilde is very large. And that can be expressed by this probability, the probability that p is smaller than p tilde minus some delta. So this will be p tilde minus some delta. Actually, there'll be an n, and p is still smaller than that, and that's captured by this term. And these are the two ways in which p tilde can be too far away, and these two events, their probabilities when summed up should be at most some small gamma. So you can think of these two events as being the bad events, and we want to upper bound their probability. So let's focus on one of the bad events. So let's in particular focus on this particular bad event and bound its probability. Probability that p is greater than p tilde plus a delta. Well, we can rewrite that event to probability that p tilde is less than p minus delta. So we are just we're just taking the delta over to the other side, and notice that, or at least recall that p tilde times n is your x. So in other words, x equals x by n is p tilde, and that's what we're going to do here. We're going to replace p tilde with x by n, except that n we're going to take it over to the other side. Okay, so now we're close to applying Chernoff bound. Recall that um, n times p is e of x. So if you pull out the p from within this within here, you're going to get e of x times 1 minus delta divided by p. And now we're ready to apply Chernoff bound, because now what we have is the probability that the binomial random variable is less than its expected value times 1 minus some quantity. And so now we can apply Chernoff bound, and the bound we will get is this one, e raised to the minus np times delta over p squared divided by 2. Okay, so we can cancel out one of the p's here. You'll get this term. This p is a bit ugly. We don't want that, but that's easy to get rid of because it's a probability, and since p is always going to be upper bounded by 1, we can actually get rid of that, and this becomes an inequality here. So we're finally left with this quantity. Okay, and that, as it turns out, is the probability that the estimate p tilde will lie in this region. In a similar way, we can bound the other alternative, the other bad event, which is that p is less than p tilde minus delta, and we will get a similar upper bound on that on the probability of that bad event, and that will correspond to the estimate p tilde lying in this range. So finally, we have two bad events. We need to get an upper bound on the probability of the union of those two bad events. So we simply apply the union bound, and that the upper bound on the probability of those two bad events should be at most gamma. So now we can get an expression for the gamma that will help us to to get a trade-off between all the terms we have. So this gamma is let's say we set it to the sum of these two upper bounds on the bad event probabilities of these bad events. So gamma is equal to e to the minus blah 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 divided by 2 plus e to the minus n delta squared by 3. These are two upper bounds. And by setting it this way, now we can clearly understand this trade-off. How? Well, let's look at it a little bit. So now let's say your boss wants you to estimate the parameter p within with a confidence interval with a 1 minus gamma confidence interval p tilde plus or minus delta. Now the question is, how many times should you how many samples should you take? All we have to do is then apply this formula and solve for n, and we will know how many times we will have to sample in order to get the appropriate confidence interval.